time. Oh, go ahead. Yeah. Yeah, you can ask the
I
question.
guess I have another question. So
Yeah, go
like,
ahead.
so is it possible to like observe like a Bose-Einstein condensate with like force carrying bosons? Uh, or yeah.
What do you mean? So we observed it, right? So we made in a laboratory,
Yeah,
have shown a bunch of pictures.
so I guess it's like so we have like in the standard model we have a bunch of like force carrying bosons like the gluon, like the WZ bosons. Like, is it possible to get like a bunch of like these particles together, cool them down, and observe like a Bose-Einstein
Oh, I see.
condensate?
Um, the I would say in principle, yes. But in the case of W and Z bosons, they are actually very short-lived. They decay right away. So in practice, I don't think you can do that. In the case of photon, the Bose-Einstein condensate is actually laser. And we will talk about that when we quantize the electromagnetic wave. So we actually use it. Whenever you point a laser pointer in your hand, then you're creating a Bose-Einstein condensate. Okay, so let me get started with the lecture today. And I hope you guys are doing okay with the midterm problems. If you have any questions, either email me, put on Piazza. I try to respond as quickly as I can. And if you ask the question personally, of course, I don't want to be unfair to other students. So I try to announce the question and answer on the B courses so that everybody has access to the same piece of information. So that's what I'm trying to respond to them. So if you have any issues, just let me know. Okay, so let me get started. And I'm actually very happy today because I got vaccinated just an hour ago at the Golden Gate Field, and everything was very smooth. I feel a little warm now. I think the immune system is working in my body, and so I'm very happy. So we talked about this BCS state, especially in the context of the superfluid helium-3. So the idea there was that we want to have some analog of the condensate for fermions. And in the case of boson, we talked about this. We create this coherent state by having this infinite superposition of different occupation numbers. And then the state starts to become coherent with a well-defined phase. And we have seen many examples of that in many pictures and data that coherent state can really be made in the laboratory. And excitations corresponded to the Bogoliubov transformation of the original boson creationization operator. In the case of fermions, we can't do this because you cannot occupy the same state multiple times, being a fermion. So what you do is instead take a pair of fermions with momentum p and minus p, so that the pair has a total momentum 0. And this pair now has a condensate. And once again, you can put the pair only once into the state. I cannot occupy the same pair twice. So this stops here. But there are macroscopic number of pairs in the system. So when you have this Fermi degenerate gas given by this red line with a step function, you look at the pairs near this Fermi surface. And because it has a finite momentum, it can orient in any possible direction. So you can have a huge number of these pairs. And you form this linear combination for every one of those pairs for each momenta. So then you again have sort of similar idea that you have a macroscopic number of pairs now condensing. So each pair has a different momentum inside, but as a whole, it's the same momentum, namely 0 momentum state. And now you can occupy macroscopic number of them. And that's the idea of the BCS state, according to Bardeen, Cooper, and Schrieffer. And Bardeen was also involved in the discovery of the transistor. So he is the only one I know of who received the Nobel Prize in physics twice. So, important guy, obviously. And so that was the idea of the BCS state. And what you're supposed to do then is, given a Hamiltonian of whatever you got, you try to minimize the energy in the spirit of, again, variational principle by using this eta, the linear combination of unoccupied and occupied pair, so that you can look for the minimum energy state by varying eta for every momentum combination. And that becomes a little technical, so I'm not going to show this, but you can see that discussion in the lecture notes for me on the PDF if you'd like to know more about it. So the idea is that when you have an attractive interaction among the fermions, then the ground state is preferably BCS state over the vacuum state. And because you take this linear combination of unoccupied and occupied, then this Fermi surface is no longer as rigid as a step function that gets a little smeared. And how much this smearing happens is within the range of energies called gap or delta. And I'll show you the idea of the gap on the next slide. And indeed, the liquid helium-3 does become superfluid as a BCS state. And once you have this condensate, then you can define a coherent phenomenon out of this. And that also shows up, I think, in 2 slides from now. So that's the idea of the BCS state. So experimentally, once you have a gas of helium-3, you cool the gas, becomes liquid. It's a normal liquid, which just doesn't have a superfluidity. But once you actually cool it even further, then you get into the superfluid phase. But there are 2 different kinds of superfluid phases in the case of helium-3 because of the spin degrees of freedom. I mentioned this briefly last time. So that's the idea of the BCS state in general. And we also apply this idea to the case of the electrons in a metal so that this actually becomes a superconductor later on. So we'll come back and talk about that too. So anyway, this is the idea I introduced last week. Let me stop here to see if there are any questions. No?
I have a question.
Oh, okay, Adi. Natalie next.
Okay. So this would never happen for a pair of electrons because they have a strong repulsive interaction. This is only happening because the helium-3 atoms have a weak attractive interaction.
That's correct.
Is that right?
That's correct.
Okay.
Yeah. But when you actually put electrons in a material, there can be actually an attractive force, and that would lead to the superconductivity. So we'll come back and talk about that. Thank you for the question, Adi. Natalie?
Why did you say there's a smearing of energy states?
So if you look at the how many particles are occupied for a given momentum, so this particle with momentum p is not 100% occupied because you have a linear combination of this vacuum state, not 100% vacant because you have this linear combination of the occupied state. So it's neither 0 or 1, so halfway between. So that's this blue curve. So it's not 100%, it's not 0%, somewhere in the middle with a finite probability of occupation. And that corresponds to sine squared eta as a probability of having the particles occupied. And that's how this gets smeared from this rigid step function in red to this smooth curve in blue. So that's what I meant. Does that answer your question, Natalie?
Yeah, and the reason why it's not present in BECs is because it's a coherent state that describes energy states.
Oh, no, this actually happens with the BEC state too. So zero momentum state is now this coherent state, and non-zero momentum modes become this Bogolyubov transformation. And Bogolyubov transform state is again a linear combination of unoccupied and occupied. And in the case of boson, of course, occupied can mean 1 particle, 2 particle, 3 particle, ... So you have the big linear combination of all of them. So again, occupation number is not rigid step function, it's somewhat smeared in a similar way.
Okay.
Okay.
Thank
you for the question. Any other questions here? Okay, so let's see how that works in practice. So here's some kind of Hamiltonian. So I'm not looking at the entire Hamiltonian of all the atoms in the system. I'm just singling out the piece for the particular momentum P and minus P. And here's this attractive interactions among them. So this quadratic term again is meant to be interactions among particles. And you have done, you're doing this exercise now in the midterm problem, that general potential eventually comes to this kind of form. And so the idea is, how do we come up with the ground state of this system? And so what you do is to assume that there is some kind of condensate, this pair condensate. And this is a pure assumption at this stage. But once you work out the consequence based on this assumption, you want to see if that will actually minimize energy. And then you find the ground state as a candidate, and you compute the condensate using that ground state to see if this is self-consistent. So the idea is that you are looking for self-consistent solution, postulating the condensate, minimize the Hamiltonian, work out the ground state, and then you compute the condensate with the ground state and make sure that they agree. And so that's the method of self-consistency. So first thing you do is make an assumption that there isn't a condensate. Then you can look at the quadratic piece in this Hamiltonian by replacing B dagger with a condensate delta, BB with a condensate delta. So now you have these pieces, which is quadratic in B and B dagger, but it's off diagonal in the sense that this is not B dagger B, it is B dagger or BB. And of course, they are still fourth order term in Hamiltonian, but we are making this approximation, namely the same thing as linearization you have done in the homework problem before. We are keeping the lowest order pieces and understand what's the consequence of that. So in some sense, I'm ignoring the quadratic piece relative to this delta piece, and we got the remaining, this fourth order term as a small perturbation to the system. So we go ahead and diagonalize this Hamiltonian. And as you have done last week with the homework problem, if you have a Hamiltonian, which is only quadratic in B and B dagger, you can always diagonalize it by Bogoliubov transformation. And that's something you have done last week. So it turns out the same idea also applies to fermions. So this is still quadratic order Hamiltonian. B dagger B is quadratic, B dagger B quadratic, B dagger, it's a weird term, but it's also quadratic. BB, also weird, but quadratic. And whenever you have a Hamiltonian, which is quadratic in B and B dagger, then you can diagonalize it. And so that's what we are going to do. So this book,
Professor,
go ahead.
Oh,
Yes.
Sorry to interrupt. So what you mean by we postulate that there's a pair condensate is that we assume that there is expectation value is non-vanishing?
Yeah, that's what I meant. Yeah. So when I said postulating condensate, what I meant was that expectation value of DBB combination in the ground state is non-zero.
Okay.
And assuming that this is non-zero, I can now justify replacing this BB by the size of the condensate. So V times BB is delta. So that's delta here. And I'm writing the remaining B dagger, and that's the first term. And Hermitian conjugate of this is the condensating B dagger. So V B dagger is replaced by delta star, if you want to be accurate, and times remaining BB. So here I assume the delta is real. That's why it doesn't have a delta star in it. But if you want to be really precise, this could in principle be complex. So this piece comes with delta, second piece comes with delta star. Okay? Thank you for asking the question, Reddy. So here's a quadratic Hamiltonian. You can always diagonalize this with a Bogoliubov transformation. But it's the difference from the boson case is that it's not hyperbolic function, but a trigonometric function. Instead of cosh, I have cosine. Instead of sinh, I have sine. The reason for it is that you want to make sure that the canonical anti-commutation relation is satisfied. For example, two C's should anti-commute with each other. And when you compute the anti-commutation relation between two C's, the piece that would in principle remain is this piece between B and B dagger that comes with cosine and sine, and also a piece with B and minus B dagger that comes with cosine and minus sine. And so with this minus sign, this cancels. So that's why this Bogoliubov transformation is okay. It preserves the anti-commutation relation so that the two C's anti-commute. You also want to make sure that the C and C dagger has an anti-commutator of 1. And again, if you want to compute this using B and B dagger, C has piece BP, C dagger has minus B dagger, so this is C, B and B dagger anti-commutator. No, what I'm saying here. No, I'm sorry, I misspoke. I'm computing anti-commutation relation of C and C dagger. So I take B here, and dagger of the whole thing. Dagger of the whole thing has B dagger P in it with a cosine. So I get cosine squared eta. I also have this B dagger of minus P with sine. Then the Hermitian conjugate of that has B times sine eta. So that gives you undecommutated 1 with sine squared eta. So that's how I end up with cosine squared plus sine squared, that's 1. So that way we preserve the same anticommutation relation. So that's how new C and C dagger have the interpretation of creationization operator of the fermion. And then what you like to do, make sure is just like what we have done with the boson in the previous homework problem, you make sure that there's no term that looks like CC or C dagger by choosing the correct angle eta. And that choice of the angle turns out to be, I'm sorry, this is typo, tangent, not tangent of 2 eta is delta over E naught. And once you actually use this eta and plug that back into Hamiltonian, you find this energy of square root of E naught squared plus delta squared. So that's how you have now diagonalized this Hamiltonian. And now that the Hamiltonian is diagonal, you can also write out the ground state explicitly. And that ground state turns out to be this linear combination of unoccupied state and a state occupied by the pair with the same angle eta. And hence, this is the BCS state. So the idea of self-consistency I mentioned is now that I have the ground state, I can compute the condensate using this ground state. So that actually turns out to be negative sine eta cosine eta. And knowing that this is the size of the ground state, you want to make sure that this value of the condensate really is consistent with the size of the condensate I assumed, namely delta, and that's the idea of self-consistency. So once you have postulated this condensate, you work out the Hamiltonian, you find the ground state, then you compute the size of the condensate using the ground state you got, namely BCS state, and make sure that what you computed is the same thing you started out with. And that's how you can fix the size of the delta at the end of the day. And that consistency equation is called the gap equation. So that's the idea of the BCS theory. You don't know a priori that your Hamiltonian prefers a finite expectation value of BB or condensate, but you assume it. Assuming the condensate, you minimize the Hamiltonian, and then you can work out what the ground state is. Using that ground state, you can recompute the size of the condensate, and then demand that the size of the condensate now you computed with your ground state agrees with the size of the condensate you assumed at the beginning. And that self-consistency is the gap equation. And the reason why it's called gap is because this actually turns out to be a gap in the energy spectrum. So looking at this energy eigenvalue, E naught squared plus delta squared, there's a minimum, namely when E naught, which is the kinetic energy minus the chemical potential, is 0, which corresponds to the area near the Fermi surface, E naught can vanish, but delta cannot. So your Hamiltonian has this finite gap of delta. And that's why this delta is called gap, which has dimension of energy. And that really corresponds to how much energy has a gap in the spectrum. And the self-consistency of the size of the gap is this gap equation. And when you solve the gap equation, you know what the gap is at the end of the day and what BCS state you are talking about as the ground state. So that's the idea of this BCS theory. So it may sound sort of roundabout way of obtaining the ground state, but this is turns out to be the cleanest way of obtaining the ground state based on this variational method. And an actual gap equation looks kind of complicated, so I don't write it here. But again, you can find it actually in the lecture note, fermion.pdf. Okay, so that's the argument. So let me stop here. I'm sure you have questions about this. No, that's surprising. Sure. Or are you totally lost? I hope not. Does it make sense? Okay, I see Riley nodding. So at least it made sense to some people. All right, so let me go ahead. And again, if you have any further questions, we can always come back. So it turns out that once you have this pairwise condensate, that is also something you can describe using the Schrödinger field. So in the case of the BEC, you have a condensate of single particle. And so you have a expectation value of annihilation operator. It's actually a eigenstate of the annihilation operator. That's a coherent state. And then you can define a field which has a value now. And we could use the classical field theory to describe it. So that was this amazing particle wave duality. In the case of BCS, you have a pairwise condensate. So if you compute the expectation value of a single annihilation operator, it vanishes. But if you have a pairwise condensate, you can compute this pairwise expectation value. Namely, you put in the annihilation operator for P, annihilation operator for minus P. That pair has a condensate. So you can define a bosonic field by computing the expectation value of pair of the fermion annihilation operators. So this is what is called the Cooper pair, which is C in BCS theory. So he came up with this idea that if you have a Fermi degenerate C, but some form of weak attractive force among them, then they actually form these Cooper pairs, and the Cooper pairs condense as if it were a boson. So you can define this composite field rather than elementary field. Of course, in the case of the Bose-Einstein condensate of co-atoms, atom is a composite object too. So in some sense, it's similar. So everything is composite in this context. But difference here is that you're talking about tightly bound boson condensing its own, that's the BEC, versus loosely bound fermions condensing as a pair, that's the BCS. And obviously, two ideas are continuously connected. If you try to jack up the binding energy between two fermions, loosely bound BCS state eventually becomes a tightly bound boson that condenses. So they are smoothly connected, and that's the idea called BCS-BEC crossover. And people have done an experiment, again, dialing some knob of magnetic field or something, so that system can smoothly go from loosely bound BCS to tightly bound BEC. So they are indeed continuously connected. So there is no sort of a big surprise that you can describe BCS state also using a bosonic field because they are continuously connected anyway. And so, especially when you're working at the energies or temperatures below the dissociation energy of this pair, so in the case of the previous slide that corresponds to the gap, then you can treat bosonic field as a single entity, and you don't need to worry about this getting dissociated when you're working at the low enough temperature. And so that's how you can write down the Lagrangian. And in the case of the superfluid helium-3, you can have this liquid in any reference frame you want. So you still have this idea of Galilean invariance. And Galilean invariance then dictates that your Lagrangian should have the form we have used already many times. So hence, this Lagrangian should describe the superfluid of helium-3. So the idea of using the classical field theory is once again useful even for fermions, but interpretation is now different. Field psi is this field psi b, which is meant to describe a pair condensate of fermions. So each psi can annihilate a pair of two helium-3 atoms because it's twice the field. But using this field, you can treat it as if it's a classical field. And again, talk about the same thing we have done. You can talk about the ground state with a condensate. You can talk about the constant flow as a superfluid. You can talk about the persistent current in a donut-shaped tube. Or you can talk about vortices in helium-3 superfluid. And all of these ideas, again, would carry over because mathematically, it boils down to the same classical field theory. So that's the idea of the BCS state, describing a pair of fermions. And in the end, you can use this classical field theory now we have gotten very familiar with to describe the superfluid of helium-3. Okay, let me stop here. I'm sure that you have questions.
You said earlier that electrons can form Cooper pairs, yes?
Mm-hmm.
So I'm trying to resolve the mental picture in my head, and would it be wrong to imagine that these Cooper pairs, given that they have opposite angular momenta, would have to almost rotate around each other? Because that would
that's
be
right,
the only
yeah. Yeah, that's right.
Does that mean that then there's some form of angular momenta associated with the Cooper pair, and so there could be some form of split degeneracy caused by maybe magnetic field or electric field applied over to these Cooper pairs?
That's actually a very good question, and that's indeed the case. And I didn't show that slide this time because I didn't want to get too much into detail about the helium-3 today. The main focus is going to be a superconductor. But this is a slide I showed last Friday. And helium-3 is a fermion. That's what I'm trying to explain here, and that's taking some time. But the two form a wave function between two fermions. Of course, we have to make sure that that's antisymmetric. And there are several ways of doing so. And it turns out that the helium-3 chooses this relative orbital angular momentum 1. So as you said, Earl, they are circling around each other with a finite orbital angular momentum. And the orbital angular momentum 1 has this spherical harmonic, which is the antisymmetric under the interchange. So that's -1. And then that requires the spin part of the wave function has to be symmetric. And 2 spin 1/2 symmetric wave function is spin 1. So this is a situation that spins are aligned and then they circle around each other. And then there's a choice of what the total J would be. And total J has the option of 0, 1, and 2. So namely that the L part of the wave function has 3 possible states, 1, -0, -1. S part of the wave function also has 3 possible states, 1, 0, -1. And they form a 3x3 matrix Schrödinger field. So Schrödinger field has now multi-components. There are 9 Schrödinger fields altogether. They are arranged in a 3x3 state combination. And you write the Lagrangian for this 3x3, and you introduce interactions. It turns out that there are 2 possible interactions among 3x3 matrices. And depending on the relative size among them, then you can have different component with a condensate. And that's how the helium-3 has these 2 different phases of the superfluid, phase A and phase B. So it's a very rich theory, and that had been worked out by Anthony Leggett, and he received Nobel Prize for this theory. So 2 phases of helium-3 is attributed to different components of these 3x3 matrices. And depending on the temperature and pressure, 2 different attractive forces can have different relative sizes and preferring different kind of condensates for the ground state by just minimizing the potential energy. Okay, does that answer your question, Earl? Good, good. So it's fairly complicated, but rich theory, and that's why you have these 2 different phases of the superfluid. Thank you for the question. Any other questions on the next slide when actually got to this composite field?
I actually had a question about the previous slide.
Oh, previous slide.
I was just wondering if, yeah, the transformation one. I was wondering if you could just explain again how you're expanding the expectation value into the sum of operator products.
You mean this interaction potential?
So once you set delta equals V times that expectation value, how do you get to the next line?
Yeah, so I'm replacing this V in the Hamiltonian times these 2 B's by the expectation value delta. And then that leaves 2 powers of B dagger as delta B dagger B dagger. So what we would like to do is the Hamiltonian something we can analyze. And we know how to deal with quadratic Hamiltonian of the B and B dagger operators. We don't really know how to deal with a quartic fourth power term like this one. So this is an approximation method that, assuming that there is a condensate, I can turn this quartic term, which I don't know how to deal with, into a quadratic term I know how to deal with, to the extent that the remaining quartic term can be ignored as a small perturbation. Then I can diagonalize the Hamiltonian and obtain the ground state. So idea is to try to come up with an approximation method where I know how to deal with quartic ones I don't know how to deal with. But if I assume a condensate, this quartic Hamiltonian turns into quadratic Hamiltonian together with additional interactions which I'm ignoring. And then I know how to deal with this. I can diagonalize it. And when diagonalize the Hamiltonian, I have this free parameter delta, which I just postulated. I don't know the size of it. So I choose delta at the end of the day to minimize the energy. And that's how I can obtain the ground state. But that ground state need to reproduce this condensate I initially postulated. So that's a self-consistency requirement. And that's how we can fix the size of the delta in a self-consistent fashion. Then I'm justifying this Hamiltonian, quadratic Hamiltonian at the end of the day. So everything makes sense. So that's the idea of how to deal with this Hamiltonian. Does that answer the question, Shrek? Okay, go ahead.
Yeah, it does. But I think I'm just like, so the last term in the equation, the B minus P BP, why is it fair to assume that there's no prefactor for that term? Because that's sort of like the perturbation term.
So this BB is part of this parentheses. So this BB is also multiplied by delta. So here I'm replacing V B dagger by the complex conjugate of this delta. I just assumed in this Hamiltonian delta was real. So the delta star is same as delta. So delta star BB is what is part of the Hamiltonian here. And assuming delta is real, I just put them together into a single parentheses.
Okay.
Is that what you're asking?
Yeah, I think that answers it.
Okay,
thanks.
Good. Any other questions?
Yeah, why do you keep both terms? When you do the substitution once, doesn't that already kill two, for example, if you just do the delta equals V expectation value of B minus P BP, doesn't that already kill the B minus P BP, and then you're just left with the B daggers? Why do you have to do it like twice, and how do you get two terms out of that?
Yeah, that's a very good question. So this is again in the spirit of perturbation theory. So we are treating this attractive interaction to be weak. Then the lowest order term is that all condensates are replaced by numbers. That's a zeroth order term. So this B dagger is replaced by delta over V. This BB is replaced by delta over V. Then the whole thing becomes just a number, delta squared over V. That is what I regard to be the lowest order in perturbation theory. So it's a number, so maybe you don't care, but it is of the order of V delta square over V. So to the extent the V is small, delta square of V is large. That's why that's the lowest order term in expansion. Then next order in expansion is that I now look at the deviation of BB away from this condensate. So I write BB to be expectation value plus the perturbation BB. And that's in the same spirit when you actually expanded the field in the boson Schrödinger field equation, took the linear term and could identify the spectrum of the excitation. And it's the same spirit. We are expanding everything around the expectation value. And the deviation from the expectation value is the perturbation to the system. And you do the systematic expansion of that perturbation. So I have to replace both this BB as expectation value plus perturbation BB, as well as this B dagger as expectation value plus deviation from the expectation value. So I'm doing the expansion in both. And the product of expansion from both terms would be of the order of V, and that is supposed to be small. So that is the quartic term I'm ignoring. But the cross term between perturbation and the condensate gives you these two terms. That's order delta. It doesn't have V in it. So that's the lowest order expansion, which I have to keep. So in the spirit of perturbation, the lowest order term was condensate, giving you constant. That was order delta squared over V, that was large. And the first order in deviation in BB or B dagger gives you these two cross terms. That's order delta I'm keeping. But the last term is B dagger BB of order V. Because V is small, I'm dropping it. And that's how I justify this quadratic Hamiltonian. Does it make sense, Adi?
Yeah, thank you.
Great, and thank you for the opportunity that I can actually clarify this, because I didn't fully explain that this was indeed in the spirit of perturbation theory by expanding these operators around the expectation values and looking at the deviations as a perturbation to the system. Thank you. Anything else? Everything good? Yep, so this self-consistency would eventually determine the value of the gap, correspondingly, the value of this Bogoliubov angle eta, correspondingly, ground state, given in terms of this Bogoliubov transformation, that is supposed to minimize the energy, and at the same time, that is supposed to reproduce the delta. So that's the self-consistency, and the system can be then solved using this self-consistency, and that's the idea of the gap equation, which in the end fixes the size of the gap in the energy spectrum as seen by this quadratic Hamiltonian. So that's how you actually solve for the problem. And then that is done in this composite field I mentioned, and then you can write the field Lagrangian for this composite field psi b, and the Schrödinger invariance dictates the Lagrangian has to look like this. And then we can apply the same analysis we have done to look for the static solution, the constant flow solution, persistent current in a donut shape, and vortices, and all of these things will follow also for the case of the superfluid helium-3, just like in the case of the helium-4 and the cold atom systems. Now we switch to electron, and that's the one some people are asking about, like Earl, I think. So electrons normally repel by the Coulomb interaction. So you don't expect electrons to become BCS state. But situation could change when electrons live inside some material. So the idea is that if you take certain metal like mercury, you have these isolated electrons moving almost freely inside the metal, and they basically form this Fermi degenerate sea at the room temperature. We talked about that before. But it turns out that these electrons have a very weak repulsive force, because when you place an electron, lattice is formed by the ions. Ion is positively charged because they have lost electrons. And positively charged ions get attracted to the electron. So the lattice would deform a little bit so that ions come closer to the electron. And as a whole, it looks like this region has attracted a positive charge. So overall, this electron, if you look at it from far away, looks like it's weakly positively charged because of the ions coming close to it. And because this electron with this lattice deformation looks like it's weakly positively charged from the electron far away, this far away electron gets attracted to this electron. So electrons themselves, of course, repel by the Coulomb potential, but each electron basically carries this cloud of the ions with positive charge around it, so that this electron looks like it has a weak positive charge from the point of view of the other electron, and that's why they are weakly attracted to each other. So this doesn't happen by electrons alone. It happens because of this interaction of electrons with the lattice. And lattice deformation is basically a kind of sound when the sound wave propagates through the system. That is a lattice deformation. And that's why we call this electron-phonon interaction. So lattice vibration is also get quantized, and that becomes the phonon. the particle of sound. And interaction of the electron and phonon gives you an attractive force between two electrons. And that's how the electrons can form the Cooper pairs once you go to low temperatures. And this pair of electrons now has charge -2e. So now we are talking about the condensate of the BCS state that carries electric charge. That was not the case with helium-3. Helium-3 is a neutral atom. You have this BCS state of a pair of fermions condensing to become a superfluid. And then the current can flow without resistance, viscosity, friction, and that was a supercurrent. But now we have the condensate with electric charge. So when you have a solution where this pair is moving, then that current has an electric charge, and therefore that's an electrical current. Now you are talking about the electrical current with no friction and viscosity. Therefore, there's no electrical resistance to it. So conductivity is infinite. There is no resistance to this electric current, and hence superconductivity. So instead of talking about superfluidity, when the condensate doesn't have electric charge, now we are talking about superconductivity, because you can carry electric current without resistivity, and hence superconductivity. And then what you're supposed to do again is the same thing. You bring in the Schrödinger field to describe a pair of electrons, and you write down the Lagrangian. But one thing we need to do in addition to what we have done before is to make sure that this Schrödinger field correctly couples to electromagnetism. So we need to do a little bit of exercise on the next few slides, trying to learn how I can write a field theory with electromagnetism in a consistent fashion. So that is a little technical discussion about something called the gauge invariance of the electromagnetism, which I believe we have seen in classical E&M class. So I have to implement the gauge invariance into the Schrödinger field theory to make sure the electromagnetism is coupled to the field in a consistent fashion. So that's what I'm going to do in the next few slides. But the point is really here. If you take mercury and if you cool the system down to a temperature of 4.2 Kelvin, again, we're talking about rather low temperature, then the resistance to the electric current in a piece of mercury just goes down to 0 and no resistance. And that's the superconductor. Zero resistance means that you can keep letting the electrical current flow through the metal, in this case mercury, without resistance. The current, electrical current, keeps flowing. And so that's actually something very useful, of course, when you're trying to build a magnet, the electromagnet, and try to produce a very large magnetic field. You want to make sure that the electrical current that produces the magnetic field can flow very efficiently. And if there's no resistance to it, then the electrical current keeps flowing forever, and then you don't have any power loss. And that becomes a very efficient superconducting magnet. And if you go to a Large Hadron Collider, you have this very high energy beam of proton being bent inside the tunnel, circular tunnel, that requires a very high magnetic field of 8 Tesla. And you need a superconducting magnet to do so. So they are actually using an niobium titanium for this purpose, which again also becomes a superconductor. So you have to cool the entire accelerator to a very low temperature. So it turns out that inside this dipole magnets in the LHC, the beam is going through this superconducting magnet cooled to something like 2 Kelvin, which is colder than the outer space, which is 2.75 Kelvin by the cosmic microwave background. So that's the phrase you might often see. Inside the LHC, it's colder than outer space. And that's because they are using this superconductor to efficiently produce magnetic field, very strong magnetic field, without loss in energy by using this superconductivity. And so that's the thing now we would like to understand using the quantum field theory. Okay, so let me stop here again to see if there are any questions.
Oh, I have a question from last slide, from the previous slide.
Trying to go back to the previous slide. Here.
Yeah. So it says that the Galilean invariance of the system requires that the Lagrangian is the Schrodinger field Lagrangian. But is that just the simplest case of a Galilean invariant Lagrangian, or can another Galilean invariant Lagrangian also describe like a BCS or BEC system?
Yeah, so that's an excellent question. So in the case of the superfluid helium-3, you can imagine that helium-3 is sitting there in outer space with zero gravity, and you are passing by it with the rocket, and it should be the same physics. So it has to be Galilean invariant. So there's no choice. You have to impose Galilean invariance. But in the case of the electrons in the middle, then there's actually rest frame of the lattice. So the system is actually not Galilean invariant. So there could in principle be other terms that are not allowed by Galilean invariance. For example, this derivative here, delta del del del, it take the inner product in a way that's rotationally invariant, but the lattice is not rotationally invariant. So you could have a term like del x del y, for example, due to the lack of rotation invariance in the system. So in principle, you have to also put those terms in to analyze the BCS state of the electron. For simplicity, I'm using this Galilean invariant Lagrangian for the rest of the discussions. But in principle, you should allow for additional terms, which is now possible because the lattice breaks both translational, rotational invariance, and also Galilean invariance on top of it. So in principle, there are more terms you can write in your Lagrangian. So that's a very good question, Riley.
Thank you.
Any other questions? Now going back to the slide we just had on the superconductivity. And of course, kind of dream people have using the superconductor is to design a power line in the grid system using superconductor. Then you can transmit power from power station to your home without any power loss at all. And that will be, of course, is a very good thing to do. So to make the energy more green and good for the environment, eventually we would like to switch to a superconducting grid. It is still under development because if you require very low temperature, then there's a competition of cooling the power cable down versus getting more efficient transmission. Which way you win is not totally clear. But if you can have a superconductor with much higher the superconducting transition temperature, critical temperature, a dream is if there's a superconductor at a room temperature even, then you don't need to cool the power lines. Then you can really build an entire grid system using superconductor, and that will be, of course, much, much greener than the current the power system, which miserably failed in Texas lately. So we really have to fix that system somehow. And so going to a superconducting grid is sort of the dream of the future. Okay, that's a side story. Oh, go ahead.
I do, yeah. On this slide, a quick question that I kind of had is, I remember you said something like like in the point of view of like one electron, like it was like the electron was like positively charged and attractive or something. Can you kind of explain that? I didn't really understand.
Yeah.
Logic.
So the idea here is that if you have a undistorted lattice, then it looks like the uniform sea of positive charge. And that's also canceled by the uniform sea of electrons. So uniform lattice is basically the electrically neutral situation from the point of view of electron far away. Now you put electron here, and then lattice get distorted because the positively charged ions get attracted towards the electron. So if you look very locally around here, then you have sort of a higher density of positively charged ions. So relative to the uniform situation, this looks like an excess positive charge. So from the point of view of electron far away, this excess positive charge would attract the electron. And that's how they start to attract to each other. So each electron carries this sort of cloud of positive charge around it due to lattice deformation. And that's how they started to attract each other to form these Cooper pairs. Am I answering your question?
Other electrons see other electrons as like positive charge. So these two electrons would actually want to come together because they both see each other as positive charges.
Right.
And that's
But when they,
okay. And then they form.
yeah, exactly. But when they come
But
too
wouldn't-
close with each other, the electron would think, oh, I was cheated. This is actually an electron. I'm supposed to be repelled by it. So that's why it becomes a sort of very weakly bound situation. They stay fairly far away from each other, but they are nonetheless forming this pair.
Okay, yeah, because I was gonna say like, yeah, because then if they're both positively charged and they're like attracted, wouldn't they like repel because they're both large positives? So wouldn't they actually want to be farther away from each other?
So from the point of view of the other electron, so of course the positive charge are being attracted to it, but electron itself knows it's negatively charged, right? So from the point of view of the other electron, it sees the sort of overall charge of the other electron, which is now screened by the positive ion, and has even become positive slightly because of this distortion. So that's what the other electron sees. The other electron itself knows it's negatively charged, but it now sees the other electron to be slightly positively charged. Am I answering the question? Okay.
Yeah, I think.
All right, good. So that's why
Oh.
they become Cooper pairs and they condense and become BCS state. Sorry, go ahead.
Just to build off this question,
Uh-huh.
so the lattice vibration caused from the ions feeling the negative charge of the electron,
Mhm.
that is what is like the electron phonon interaction.
Yes.
Is that true? Okay.
Yes, it is.
And so could you explain a little more about the like phonon? Is that
Yeah,
just caused by the vibration of the
Mm-hmm.
lattice deformation?
That's a very good question. And this actually requires a little bit of discussion that would happen towards the end of this course. But if you think about, so forget about the lattice for now. Then you have just electron, another electron, and they repel by the Coulomb interaction. We end up describing the Coulomb interaction in fully relativistic QFT based on the idea that electrons can emit a virtual photon, and the other electron absorbs that virtual photon, and that is actually the true nature of the Coulomb interaction. So we come back and discuss this idea later on. So the forces, of course, don't act instantaneously in a relativistic theory. Something has to go from point A to point B to exert forces, because nothing can go faster than the speed of light. So the idea is that if you have one electron moving somewhere at point A, it emits this virtual photon. The reason why we say virtual is that it doesn't satisfy energy momentum conservation. But quantum mechanics allows us to violate energy momentum conservation for a short period of time within a certain principle. So you can actually do that in a quantum theory. But as long as this virtual photon is absorbed by the another electron so that it would disappear from the system, you can go back to the situation where energy momentum is conserved. So one electron comes in, emits a virtual photon, and as a reaction, the electron receives a kick. So electron changes direction by emitting a virtual photon. That's a situation energy momentum is not conserved. But when the other electron comes and absorbs this virtual photon, it receives the kick, that's the action, then it goes off in a different direction. And if you compare the initial configuration and final configuration, that is the scattering process. Because electron came in one direction and now moving in the other direction, it changed the direction, that's a scattering. But this scattering is caused by the exchange of the virtual photon. The way we used to describe this in quantum mechanics is by saying, well, there is a Coulomb potential between them, and that's what causes the scattering. But then you are subtracting from the idea is that there is a static Coulomb potential that acts instantaneously over distance, which is, of course, not allowed in relativity. So instead, once you go to relativistic QFT, you replace this idea of static Coulomb potential by the exchange of the virtual photons. So in general, the idea of force is replaced by the exchange of virtual particles. So that's the way that the forces are described in relativistic quantum field theory. Having said that, we are talking about here non-relativistic system. But the idea is actually the same. when you have an electron, that causes the deformation of the lattice. And when the deformation of the lattice propagates through the system, that's a sound wave. And sound wave is now quantized into a collection of phonons. And the way you describe this attractive force between electrons is the same thing. Once you have an electron coming in, it can emit a phonon now. And phonon is virtual. But the other electron absorbs the phonon. And as long as that happens within a finite time, it still satisfies the energy momentum conservation within the uncertainty principle. So that's allowed. So now you're talking about forces between two electrons by the exchange of virtual phonon. And that force turns out to be attractive. That is the most correct way of describing it. So here, this picture I'm drawing here is a cartoon way of explaining how lattice deformation can give you an attractive force. But when you would like to actually compute this effect, you first understand how electron would deform the lattice. That is the electron-phonon interaction. Then you can exchange a phonon between two electrons. You compute that process. Then that process is now understood as an attractive force between two electrons. Then you write this attractive force into a Hamiltonian in electron. Then you go through this BCS analysis to minimize the energy. And that is how you find the superconductivity. So it's again, fairly long story, but idea boils down to the fact that if electron interacts with the phonon, exchange of the phonon would give you weak attractive forces between two electrons. And then that is the cause of this instability of the Fermi surface, giving you a condensate. And then you find this BCS state of superconductivity. So that's the condensed story of how things work. And again, we'll come back and talk about this idea, how the exchange of virtual particles is actually what causes the force among elementary particles. We'll come back and talk about this. So we sort of went ahead of ourselves here, but I hope that will answer Riley's question.
Yeah, that did. Thank you. That makes sense.
Great. And of course, when you open textbook of superconductivity, it always talks about this electron-phonon interaction as the origin of the BCS condensate, and that's where it's coming from. And the fact that we actually know that this is the cause of attractive force is by looking for something called the isotope effect. Suppose you have mercury with a given isotope, and where you also study mercury of a different isotope, then electron-phonon interaction would be different from each other because the mercury nucleus has now a different mass because of a different number of neutrons, right? And then people observe, but indeed, different isotopes would exhibit different the critical temperature as a result. So that's how you know that this superconductive phase transition really has to do with electron interacting with the lattice, namely electron-phonon interaction, and that's how BCS theory had been proven at the end of the day. Okay, any further questions about this?
Yeah, I have a quick question.
Go ahead, Adi.
So what metals can do, like, is it, you say in certain metals, for example, mercury, what determines which metals can be superconducting and which can? Is it like the lattice deform, like the nature of the lattice deformation, or something else? Or?
Yeah, so you need to understand the interaction of the electron and lattice, and obviously, depending on different metal or different material, lattice will be different from each other, so they have different properties. So whether electron-electron interaction would end up being an attractive force strong enough to destabilize the Fermi surface is material dependent. So that decides whether a certain material becomes superconductor or not.
Thank you.
So the whole idea is very universal, but whether that happens or not depends on the material. And that's why different material has very different critical temperature for the superconducting phase transition. And the people are really looking for a room temperature superconductivity by choosing the right material. So we all are hoping for that. Okay, any further questions? Okay, so I hope the story at least is now in your mind, how superconductivity happens. And then comes the technical part. How do we write the Schrödinger field theory, coupled to electromagnetism in correct fashion? And that brings us to a discussion of the gauge invariance of electromagnetism. So this is the slide I have shown you some time ago. So modern view of QFD is that we specify symmetry of the system. So in our case, for simplicity, we are assuming translational invariant, rotational invariant, Galilean invariant system. We introduce fields, that's this Bose field of the describing the Cooper pairs. And then we write down the most general Lagrangian invariant under the symmetries. We got that already. But the part we haven't gotten already is what symmetry is there in describing electromagnetism, and how do we write Lagrangian consistent with that symmetry, namely the gauge invariance. And then we write down the most general Lagrangian, specify coefficients, and then quantize the Lagrangian and get the quantum system at the end of the day. So that's the steps we'd like to follow through now. So what are the symmetries of the electromagnetism? And that's the idea of this gauge invariance. And when you write the field strength of electromagnetisms using vector potential and scalar potential, I'm sure you have seen this elsewhere. So the electric field is negative grad phi minus time derivative of the vector potential. Magnetic field is the curl of the vector potential. So that's how you write the field strength. And there is actually a redundancy in how to write the scalar potential and vector potential for a given field strength E and B, and that is what is called the gauge invariance. So suppose you already have a scalar potential and a vector potential that would reproduce electric and magnetic fields you are interested in. But if I change the scalar potential phi by time derivative of some arbitrary function chi, and using the same function chi, I also change the vector potential by the gradient of chi. If I do that, then electric and magnetic fields are still reproduced correctly. It doesn't change. So if you look at the magnetic field, A is now changed by this grad chi, but the curl of grad always identically vanishes, so B doesn't change. In the case of the electric field, phi changes by chi dot, so that gives you a change of grad chi dot. A changes by grad chi, his time derivative. This also changes by grad chi dot. And working out the signs correctly, they cancel. So the electric field doesn't change either. So scalar potential and vector potential are not something we can measure directly, apparently, because there's an ambiguity in them. For a given electric field and magnetic field, scalar potential and vector potential have an ambiguity. And that ambiguity is what we call the gauge invariance. You can pick whatever function you like, chi of space and time, and you can change phi and A in this fashion. So now A and phi is now different, phi prime and A prime. But this set of phi prime and A prime gives you the same physics as the old phi and A did. Physics doesn't change by doing this gauge transformation. So gauge transformation is meant to be a redundancy in description or ambiguity in description. Phi and A themselves are not something you can measure anyway, so that's fine. What we can measure is electric field and magnetic fields. But for the convenience of description, in order to solve Maxwell's equation, in order to write the Hamiltonian system, you would like to use phi and A. And when you use phi and A, there's always this ambiguity in what phi and what A you pick for a given E and B by this arbitrariness given by this function chi. So chi is called gauge parameter. This switch from phi to phi prime, A to A prime is called gauge transformation. And the fact that electromagnetism doesn't change under gauge transformation is the gauge invariance, and hence electromagnetism is gauge invariant. So under the gauge transformation, field strength do not change, and equation motion of particles and Maxwell's equations are written in terms of the field strength. So physics doesn't change under this gauge transformation, and hence physics is gauge invariant. Here's the Maxwell's equations you have seen elsewhere. So they are all written in terms of electric field and magnetic fields. charge density, and current density. None of these things change under the gauge transformation, and therefore electromagnetism is gauge invariant. So that's the idea. So any questions about this?
I have a question.
Go ahead.
So this gauge invariance, does that count as like a symmetry of the system and thus have a conserved quantity by Noether's theorem?
Yes. It turns out that the conserved quantity, according to this gauge invariance, turns out to be nothing but electric charge. So electric charge is conserved because of this gauge invariance. Excellent question. Thank you for asking that. Any other questions?
Kind of building off of that, what is the symmetry like associated with that?
So the symmetry associated with this turns out to be changing the phase of the Schrödinger field. We looked at this before, and that change of the Schrödinger field leads to the conservation of the number of the particles. And for charged particle, of course, that's the conservation of the charge. But there's a main difference from what we used to do before, namely that you now allow yourself to change the phase of the field differently from one place to another in space and time. So that is what comes up on the next slide. So together with this change of the scalar potential and vector potential, which gives you this Hamiltonian Schrödinger equation in quantum mechanics, and of course we go to field theory later on, we change the phase of the wave function in such a way that that depends on space-time, because chi is an arbitrary function of space and time. This chi is different from one place to another. You are changing the phase of the wave function differently from one place to another. And that's something we haven't done before. We talked about changing the phase of psi in quantum mechanics and also in quantum field theory. But so far, we always change the phase the same way everywhere in space and time. But now we allow ourselves to change the phase of the wave function differently from one place to another. But you choose this phase together with this same chi in the gauge transformation of the scalar potential and vector potential. So this chi has to be the same function you use for the gauge transformation of scalar and vector potential. If you do that, it turns out that the Schrödinger equation remains the same. So if you replace psi by this new psi prime, which differs from the old psi by this change of the phase, but now different from one place to another, this vector potential A in the Schrödinger equation is now switched to A prime. Scalar potential phi in the Schrödinger equation is also switched to phi. Then it turns out that this new set of psi prime, A prime, and phi prime satisfies the same Schrödinger equation. And we're going to actually show that on the next slide. So here I'm just making a statement that Schrödinger equation remains the same. That's why we are allowed to do so. But what we learn is that we need to make sure that phi, A, and psi are transformed at the same time using the same function chi. And this combination of P minus EA is special because of that. So that is the idea of the covariant derivative we touched on when we talked about Galilean invariance. When you have a wave function that changes locally, depending on x and t, that was the case for the Gaussian transformation too, then you can use derivatives by time or space, the P is spatial derivative, right? In an arbitrary fashion. You need to put them together in a specific combination that the derivatives transform nicely. That's the covariance of the derivatives. And that it turns out to be a combination of P minus EA, which is the covariant derivative. Derivative needs to come together with a vector potential in a specific fashion. And time derivative also needs to come together with a scalar potential in this specific fashion. And so you are allowed to use derivatives only in these combinations so that you are guaranteed your Schrödinger equation or Schrödinger field equation later on remains the same. So what I'm telling you here is that in addition to the gauge transformation of the scalar field and vector potential, you are now forced to do transformation of the phase of the wave function psi in a way correlated to the gauge transformation you did by using the same function chi, so that you are changing the phase of the wave function in a different way from one place to another, which is a very non-trivial kind of phase transformation. And because chi now depends on space, using spatial derivative would screw up this gauge invariance. Only when you put the spatial derivative in combination with the vector potential in this fashion, you can make the theory consistent with the gauge transformation. Chi also depends on time, so only when you put the time derivative together with scalar potential in this particular combination, you are guaranteed that the physics doesn't change under the gauge transformation. So that's the idea of these covariant derivatives. So what you learn here is that whenever you have spatial derivative, P, you are supposed to put that together in a combination P minus EA. That's the only combination you're allowed to use. You can't use P alone. You can't use A alone. Always you have to put P and A together in this combination of P minus EA. Also, time derivative or Hamiltonian should come with this combination of H minus E phi. You can't use time derivative standalone. You can't use scalar potential standalone. You always have to choose the combination that IH bar delta T minus E phi as a combination. And this combination you can use, but not separately. And that's how we can ensure that physics doesn't change under the gauge transformation, where you change phi and A, but also psi this time in a consistent fashion so that physics remains the same under the gauge transformation. So that's the idea. So what we have to do is that we learn this from the point of view of the Schrödinger equation in quantum mechanics. We can apply this also for the Schrödinger field theory because they look pretty much the same, apart from this nonlinear terms in the field equation. So we can implement the same idea, same transformations, both on quantum mechanics and quantum field theory. So the thing we need to know for sure is why this combination is special. And that's the one we are going to see on the next slide. But once you know that, you know exactly how you can lift Schrödinger field theory to a fully gauge invariant Schrödinger field theory together with electromagnetism. Namely, you change all spatial derivatives to this combination. You change all time derivatives to this combination. Then you are done. So that's the idea. So we're going to see that in a few moments, but I'm sure there are questions at this stage. It is a chat. Should there be a T in the argument of the phase? Yeah, so it's implicit. This chi is a function of x and t. And here, chi is a function of x and t. That's why there's a spatial derivative. Chi is a function of x and t. That's why there's a dot time derivative. So chi is a function of x and t. I suppressed the arguments when I wrote this for simplicity. Thank you for asking that. So that was Riley. Okay, good. Any other questions?
I have a question.
Go ahead.
So when we write out the full Schrödinger field for this gauge invariant system, will it also keep the Galilean invariance and the rotational invariance?
Yeah, so that's an excellent question too. So here I'm not explaining about it. It turns out that this gauge transformation commutes with a rotational invariance, Galilean invariance, and translational invariance. So it turns out you can implement all of them at once. So that's an excellent question. We have to make sure that that is the case. When you introduce a new symmetry that might in principle screw up other symmetries you have in the system, then you are in trouble. So you make sure that all the symmetries you have in a system really commute with each other. They can be implemented consistent with each other. Then you are okay.
Okay, that makes sense. Thank you.
Thank you, Riley. Any other questions here? Okay, so the next slide is the most technical one today. So why is this combination okay? And so we just show it and work it out. So we learned that you change psi to psi prime. You also change phi and a to phi prime and a prime. So let's see what happens to this combination P minus EA. So here I'm acting P minus EA prime on psi prime. So P minus EA used to act on psi, but now I'm using P minus EA on psi prime. And we write this out. So A prime, by definition of the gauge transformation, is A plus grad chi. So I put that in here. Psi prime, also by definition, is the phase transformation of psi. And now we see what the whole thing is. This derivative acts on everything on the right. Now the psi acquires this extra phase, which depends on space. Chi is a function of x and t. This derivative can also act on chi in addition to acting on psi. So derivative acting on psi is what we had before. That's this grad psi. A times psi is what I have here, A times psi. There's a new term of grad chi times psi. But there's yet another term of this derivative acting on chi in the exponent that pulls out grad chi out of the exponent. And if you work at the signs correctly, it turns out to exactly cancel this grad chi coming from the gauge transformation of A. So you go back to the old E minus EA with the overall phase factor. Namely, when you go from P minus EA acting on psi, and you replace both A and psi consistently to new A and new psi, the only change turns out to be an overall phase factor. That's the meaning of covariant derivative. So if you go back to the previous slide, what happens here by going from the old variables, psi, A, and phi, to a new variable, psi prime, A prime, and chi prime, this A prime, chi prime here, psi prime here changes, but that actually turns out to be overall phase factor. We want to make sure that that's also true with the left-hand side of the equation. So by combining transformation of time derivative of psi and phi into this particular combination, we make sure that the left-hand side, now with E phi moved to the other side, changes by overall phase factor. Then the overall phase factor coming on the both sides can be just canceled. And then you're back to the original Schrödinger equation. And that's the way it is supposed to work. So we now have to make sure that this combination changes by the overall phase factor too. So we have now seen that under these changes, P minus EA acting on psi changes by an overall phase factor. Even if we have P plus EA another time, that also gives you overall phase factor. Now I look at the transformation of this combination of time derivative and scalar potential. So if you plug in nu phi and nu psi in here, nu phi by definition is phi minus chi dot, that's in here. But this time derivative can act on chi, which is a function of x and t, and pulls out chi dot from the exponent. That chi dot cancels the chi dot coming from the gauge transformation of phi. So you end up with the old form of del t plus IE over h bar phi acting on psi, except for this overall phase factor. So now both sides of Schrödinger equation changes by the overall phase factor. Then you can just cancel from the both sides together, and the Schrödinger equation doesn't change at the end of the day. So that is the idea of the covariant derivative. So this is true only when P is used in a combination of P minus EA. Time derivative is used in a combination of IH bar time derivative minus E phi, Only when you use these combinations, you satisfy this requirement that the gauge transformation is just an overall phase factor on the both sides of the equation. So that's how you can make sure that your theory is consistently coupled to electromagnetism, namely consistently gauge invariant. Then you can trust it and use it for the purpose of describing physics, because your physics now does not depend on what gauge you pick for the purpose of the calculation. Okay, let me stop here again. I'm sure there are questions. Chirag?
So does the choice of gauge somehow like parameterize the manifold that you're working on? Because why else would the covariant derivative be different?
Yeah, so if you choose, for example, Coulomb gauge, you require divergence of A to vanish. So if you start from some arbitrary gauge, you need to solve the equation that A plus grad chi satisfies grad A vanishing condition. Namely, you choose chi in such a way that grad A plus Laplacian chi vanishes. Then you have now gone to the Coulomb gauge. And within the Coulomb gauge, you can do all sorts of calculations. But when you would like to compare your calculation with Gerard's calculation, and Gerard happened to use Lorentzian gauge, the whole del mu A mu, namely grad A plus phi dot vanishing, that's the Lorentz gauge, then you work things out, and your calculation, your results look different from each other. But choice of the gauge should not matter at the end of the day in describing physics. So then you realize, aha, Gerard's answer should be changed to compare to Chirag's answer by changing it by minus chi dot in phi, grad chi in A, and phase factor in psi. If you remember that, it turns out that Gerard's calculation and Chirag's calculation describe the same physics. It looked different because you have chosen different gauges, but physics is the same. So that's how you make sure that the physics is gauge invariant. Am I answering your question, Chirag?
Yeah, so I think that answers it. So the gauge is like specifying a connection.
That's right. So if you have a connection, if you use the language of fiber bundle, that's the language in mathematics in geometry, then you use transition function at the overlap of different patches. And that transition function is what corresponds to the gauge transformation in physics language. Is that okay? Okay, and for those of you who don't know this language, it's totally okay. We can stick with the physics terms, but that's how you can sort of set up a dictionary between what mathematicians call versus what physicists call. And I'm already out of time, but let me just flash a slide to show how this idea can be implemented right away into the Schrödinger equation. Both sides changes by a phase, and also into Schrödinger field. Now, spatial derivative is promoted to covariant derivative. So that's a combination equivalent to P minus EA. And this is a combination, again, also the scalar potential. And when you do this transformation together at the same time, the transformation property is the same, just like in a Schrödinger equation. And so they transform covariantly. And then you can see that this piece here, the derivative on psi changes by the phase. Psi dagger doesn't have derivative on it, changes by the opposite phase. They cancel in the middle, that's invariant. This P minus EA times psi changes by a phase. P minus EA psi dagger changes by the opposite phase. Again, they cancel, the gauge invariant. And other terms don't have any derivatives in it, but they all come in a combination of psi dagger psi. So within each psi and psi dagger pair, they cancel in phase, and the whole thing is invariant. And now that you're convinced that this Lagrangian can be used for a purpose, you can just go ahead and start writing down field equations, and then you find a solution of the supercurrent. That's the current without resistivity. And then you can also see how that would affect the electromagnetic fields. And using this condensate of the field, you find that the Maxwell's equation is now modified because of the condensate psi dagger psi. And if you solve this in the presence of the Coulomb gauge, for instance, you find a solution where vector potential damps exponentially into the superconductor, and that's the Meissner effect. Magnetic field gets in, but only in exponentially suppressed fashion, and that's the Meissner effect. Magnetic field gets repelled. That's a phenomenon we haven't seen in superfluid because they were electrically neutral. But once you have a superconductor, the BCS state with electric charge, then just the Maxwell's equation tells you that the magnetic field gets repelled, namely the Meissner effect. So based on this Lagrangian, you can work out all the properties of the superconductor using this classical field theory, and that is a theory called Landau-Ginzburg theory of superconductivity. So this is what we go through the next time in much more slowly, but we have gotten the point that we have learned how to write down the theory in a way consistent with the Gaussian variance. So we go ahead and use it, write down the Schrödinger Lagrangian, couple with electromagnetism, then work out its consequences. And first consequence we get is the Meissner effect, which you probably have seen in the undergrad laboratory. Okay, so let me stop here. Sorry, I went over time for 5 minutes, and we start going back to where we ran out of time once again. So we go through this in more slowly in detail. Any further questions?
Thank you, Professor.
Thanks.
Everything okay? All right.
Thank you, Professor.
See you on Friday. Bye.
Professor.